One last little thing about the fundamental theorem of calculus. When you're doing use substitution, you do everything the same with one tiny little twist. The issue with definite integrals and use substitution is that although we never write it, it is important to realize that these numbers here, the lower and upper limit of integration, are values of that variable. More frequently than not, those are x's. In this case, it's a theta. But that means that the theta is pi, or the pi is a value for theta, and the 2 pi is also a value for theta, which is great. There's no problem with that. But when we use u substitution and say that u is the cosine of theta and du is negative sine of theta d theta, totally not a problem. We will put the negative in here to make everything balance out. We'll take the negative sine of theta d theta out, replace it with du. No issues here. And we'll take the cosine squared of theta and rewrite that as u squared of theta. Again, not of theta, just u squared. That's all well and good. The problem is that whatever numbers I put up here for the definite integral, the limits of integration, they have to be values of u. They can't be theta. So I need to make a small little fix. It's a very easy thing to do. You just have to remember to do it. What I'm going to do is make a new lower limit of integration by taking the old limit of integration, which was a theta, and plugging it in to u. So if u is cosine of theta, my new a is going to be the cosine of pi. I take that pi and I plug it into u. That way, my result is a value for u. The cosine of pi is -1. I'm going to do the same thing for b. I'm going to take my upper limit of integration and plug that in to my equation for u. I'm going to substitute the 2 pi into that theta spot, which is right there. And the cosine of 2 pi is +1. So my new limits of integration are -1 and 1, which you certainly do not have to write with the u equals. I only put it there just to show you where those numbers came from. But normally you'll see it just like this. And the great advantage to doing it this way is now that I've changed my limits of integration, I've got a definite integral in respect to u. I don't need to go back to theta at all. I don't need to worry about it. I can just take the antiderivative of u squared, evaluate it from -1 to 1, and do 1 cubed over 3 minus -1 cubed over 3. And I just realized I made a mistake. I'll have to correct in a second. So that's 1 cubed plus, 1/3 plus 1/3. Maybe somebody else caught my mistake also while you were watching. I forgot that there was a negative out here. So I do have to remember to bring that down. So there's a negative there, which means there's a negative there, which means this whole thing has a negative in front of it. So my answer is actually -2/3. And that's the answer. One more time. Quickly, we'll show you how this works. Do the next one, which looks awfully similar, but this time the u is sine of theta, and my du is cosine of theta d theta, which means since I'm changing my u, my limits of integration to be in terms of u, I need to take the old limit of integration, the pi, plug it into my u to get my new lower limit of integration, and I'm going to take the old upper limit of integration, the old b, and plug it in to my u to get my new upper limit of integration, which interestingly enough is still 0. So my new definite integral is the definite integral from 0 to 0. Cosine theta d theta becomes my du. Sine squared of theta becomes u squared. And I don't even care what the antiderivative of u squared is, because the definite integral from 0 to 0 of anything, remember, definite integral is the product of a y value times an x distance. If there's no x distance, or in this case u distance, between 0 and 0, that means I'm going to be multiplying some y value times 0. My final integral is just going to be